We are in the second session now, and welcome to the second session of this kinematics. We are going to just review pretty quickly what we did yesterday, and then we're going to do some new stuff here, like how do you do this kind of thing, comparing velocity drawing velocity vectors, comparing velocity vectors to get a change, and some special motions, and hopefully we'll have time for this, but I don't want to make this video too long, so my cut time is about half an hour, and so maybe it might go 10 minutes over. All right, so let's look at the review very quickly. So yesterday we looked at this thing called a trajectory. Let's show. So here is a trajectory. So this thing is moving this way. So this is the path, is called trajectory. Okay. So there's some points in the trajectory. So this is the trajectory over here now. So there's some points here. Oh, the P should have been here. Some P at time t, and so at some other time t plus delta t, so this is t plus delta t, and this s of t. We'll come down there a little bit later, but let's go back here. So that's the trajectory, some point p and some point q. So you have this called position at instant t. You can do the coordinates, or you can do a vector from O to P. So this is also written as O to P vector, and that's the position of P vector at instant t. And various ways of writing. It is a vector quantity because not only it's how far away from O it is, but which way in the space it's pointed when you look from O. So there's some special directions we can call. There's nothing special about it. We just pick a direction and we consider them special. Let me close this door. Okay, so special directions we pick. Maybe there was this direction is some marker here, so we can know that's our x direction. Maybe there is a building here, so we can know that's a y direction. Maybe this is another. Maybe it's another building or another thing over there. So because there's some special things we can refer to, we can go pick that as special directions, and we pick it so that these directions are 90 degrees to each other. And this is the Cartesian coordinate. Normally when we label them x, y, and z directions, we use right-hand rule. So if I go from x to y, let me show you right-hand rule, which I didn't get discussed yesterday. So I go from, so this is the x direction, and you go to the y direction, the z direction like this. So our x is I'm just the opposite of what I'm doing. So let me do it like this. So if I go from here to y, the z is pointed up for me. So you this camera is reversing my image. I have to set up later, flip it back, so the direction will be the same direction. So I see this is my right hand, and he was looking at the left hand. So maybe that's the direction. If you're a student there, my right hand would look like a left hand to you. So, but it is, you use the right hand and sweep from x direction to y direction, and thumb should point in the direction of z. This is one way of looking at it. Another way is you take this palm side and the whole thing, and that makes it xy. You know, this will be x, this will be say x, and this is some y. Maybe this x, this y, but this x and y plane is this way, and then perpendicular to that will be the z-axis. I will not do this again because this is something you should know before coming to these lectures. Okay, so there's a, at some other points was Q, and there's another position Q. This is also a vector, and the difference in the position is called displacement. So, so difference in position is called displacement. So this is the word. So it was at set time t is here, and sometime t plus some other amount of time. Can be, this could be 5 seconds, this can be 9 seconds, or whatever. This can be 5 seconds, 5.1 second. So delta t is like a time later than that, and delta t, we usually take a positive here, but we could equally talk about delta t as negative, a time earlier than when it was here. So without specifying, so displacement, what's left over is between t and t plus delta t. So this is understood. Whenever we talk about displacement, there is an interval involved, okay? Like this one is at an instance, only one interval involved. For displacement, you have two intervals. All right, so when you you can write this as a vector equation like that, or you can look at their concrete values, which will be like that. Then we talked about instant velocity. Well, the things we've talked about, but there's the instant velocity, which is can be written is written in various ways, and with an arrow over the v as a vector quantity. So this is very important. Okay, this is very important, and it's very different than what is called speed. So here, this abstract thing, this is, but concrete thing is this. So this is one number along the x direction, another number along the y direction, another number in the z direction, and this number is, we call it v sub x, v sub y, v sub z, just to indicate that we're talking about three different numbers for three different directions. And they're called components of this abstract thing called velocity vector. This is abstract. This is abstract. It's good for conceptual thinking, but this is not one number. This is, got to remember, the speed is one number. Speed at that instant is one number. It's not like those three. It measures the distance along the trajectory. Okay. So what v is doing is, so if I had a v, and you can go back to the last lecture to go more detail into this. I don't want to go in there. I need to save time for the new stuff. So it measures distance along this trajectory, and if I want to know what's the speed over here, when the object is here, I can just do this derivative. S is, say S is, you pick a point called S0 and lay out the rulers, and so 1 meter apart maybe along, so you know how much each point along the path has got a continuous value. So I can take a derivative, and if you show it mathematically, which we did yesterday, it will be related to, so this is the same thing as Vx square plus Vy square plus Vz square. So this is speed. And this is also called magnitude. So this has two names. You can say instantaneous speed or magnitude of instantaneous velocity vector. Instantaneous velocity vector. Okay. So now new step we're going to do is deriving velocity vector on a trajectory, and then changing velocity in this let's go over this. So let's start with 1. So here is a excuse me, trajectory. Here is a point P. Here is a point Q, and thing is going in 3-dimensional space that way. Excuse me. So if you do instantaneous velocity, what you'll find is when you come down here, it's a tangent. Let's see. I'm going to do a red pen. If you draw a tangent at point P, so this is tangent at point P, and this is at instant t, and this instant t plus delta t. Okay, so the velocity vector will be pointed along this direction. Okay, so this is velocity at P. So this is important to remember, that you got to do tangent, and it's often tested in tests. All right, so over here I want to know what the velocity is over there. I have to draw a tangent. This is the tangent at Q. So tangent will depend on your trajectory. Okay, and so over there is going to be along that tangent, and this is going to be at Q. Now this arrow, how long this arrow will be? The length of this arrow will be according to what's the value of this. So length of the arrow equals to speed. Okay, which is same as magnitude of this vector v. So all these things are related to so-called length of the arrow. So you really need the scales that you picked up. So you had some picked up for x-axis, like these scales 1, 2, 3, and so second is, so you need a scale for this guy too. So this guy's units will be, say, meter over second. So you need to know how big is meter per second. So let's see, if this is 1 meter, this is not necessarily the scale of meter per second. So I can pick like this big size is 1 meter per second for me. Doesn't have to be the same size, can be another size. Or I can just pick the same size as 1 meter to draw 1 meter per second. It's up to me. So let's pick some scale. So maybe let's call this, that's 1 meter per second. So over here, say this was an example of 2 meter per second, and in that direction. Maybe this, if you do it out, maybe same scale as that. Over here will be example of 2.5 meter per second. And let's see, this was delta t was 0.1 second. So it only was 1.1 second later. So we have at P, velocity looks like this. At Q, velocity looks like that. So at Q, velocity looks like that. So this is VQ, and this is VP. So this is how you're going to draw arrows on the trajectory. So these are, and the scales are marked on it. So, or you could mark the scale later outside of it. Say this, if I have this big, then going to represent 1 meter per second. So scale always goes when you're drawing arrows. All right, so that's the drawing velocity vector trajectory. So how do I know how much velocity has changed? So, so in this example here, this was a length corresponding to 2.5 meter per second, and this was the length corresponding to 2 meter per second. So what is the change in velocity? Many times students are very confused about this, and they will say, oh, I've got 2.5 and 2, so it's so what is the wrong answer, which is a common answer, is 2.5 minus 2.0 is 0.5 meter per second. This is the wrong answer. That's because velocity, this is just one, this is just magnitude velocity, it's not saying direction. So how do we actually get the velocity? How do I subtract these two guys? So I mean, this was the velocity vector, this velocity vector. So if you remember, okay, recall that you had a, from O, that was the P, and that was the Q. So this is the RP, RQ. How did you subtract? You went from here to here. That was the RQ minus RP delta R, right? That's the displacement, which was the difference of these two position vectors. So I drew from the same place these two things I want to compare. But here the velocity, this velocity is over here, and this velocity vector is at the Q. So I need to have these 2 points drawn from the same place. So, so what we do is you can just take this and translate it over here. Same direction. This didn't work out, same direction, but and same length over here. 1, 2, 2.5, 2.5, little bit longer. So this guy redrawn. You can draw this guy over there. Doesn't matter which one you put it here. Or you can draw this guy over there. Same direction and 2 length. Or you can do that. So let's see, we draw one of these. You're gonna get same picture. So VP, keep the direction same. So this is V at P, and 1, 2, 2.5 V at Q, and I want to subtract this. I would subtract this from that. So what we're going to do is start from here, just like P to Q over there. This is the delta V, or change in velocity. This is the velocity that VQ, this velocity minus this velocity. Now we use the same scale, so I have 1, 2. So look at this. This is quite a big. So if I use the same scale, so it's going to be 1, 2. It's between 2 and 3. Maybe it all depends on this angle. So this depends on the angle. Well, if this is if this was 2, this was 2, and this was 3, so you can see it's a triangle. So what will this be? You can do analytically, right? You can do analytically. So how will that be? Let's call it X. I mean, let's call it A and B Okay, so this is like a law of cosine you can use. Law of cosine. So how big this will be, this vector. And you can use a compass, and maybe you can use the same direction. You can find this angle to tell which way it's pointed. Okay, so that's how you can compare two velocities. So this is pretty hard in a way, you know. So law of cosine you probably know is if this c square equals to a square plus b square minus 2ab angle between them. So you can use that and figure that out. We don't need to do it here, but I'm trying to tell you the procedure by which you can actually do this. And sometimes this is actually asked in a test. So, so this will be a change in velocity from this much in this direction to that much in that direction. So this will be the magnitude of this. This will give you the c is the magnitude, how big a vector you need to draw in that direction. Magnitude of the change in velocity vector, change in velocity. You also need an direction of delta v. So you can pick one of the v and say, with respect to this v, how much is this direction? And that would be okay, and you need to figure that one out. Well, to figure that one out, you can figure this one out. So now, so this was theta, and this was a, this is b, this is c. And you say, I want to give you, this was my original direction. Okay, this was the v direction of vp, and I can give you this angle to tell you which way to point delta v. So this direction will be the same as this angle, the whole thing. So this direction, let's call it phi. Phi will be, and let's call it angle B, opposite to this guy. So phi will be 180 degrees minus angle B. And how do you get angle B? So in this triangle, you have a theta. You want that angle. This is A, this is B, and this is C. So you found out what C is. You know what that is. So you know this, and you know this. So it's law of sine, and you can use that to find that very easily. So like b over sine of this angle equals c over sine theta. So sine of angle B is just c of b sine theta over c. So that's where you can get the direction as well as magnitude, but just by drawing arrows and working out carefully, right? Using law of cosines and law of sines. So some of the trick you have learned actually gets used here. You know, many problems that you solve in this part of physics, especially in the contest or test, they really rely on law of cosine and law of sine for you to be very efficient in your solution. You can always do other ways, but this is sometimes you have to make a value judgment that in this given situation, is this strategy is going to work, or that strategy is going to work, and how you're going to proceed. So that's actually is up to a situation dependent. Okay, so let's change in velocity. Another way of looking at change in velocity. So change in velocity. So change in velocity. So we did with diagram. and law of cosine and law of sine. Another way is look at V at P is Vx, Vy, Vz, and this is at time t. And V at Q is going to have, it's new. So I'm going to write V of Qx equals to, so whatever it was at P plus a little bit different, okay? A little bit different. And so a small, doesn't have to miss whatever needed. So basically VQX minus VPX, I'm going to just denote by delta Vx. Just this is denote. Not a very secret thing, a very mysterious thing. Just give it a name. So VQ will be like a, you might say VPX, PY, PZ. It's going to be VQX, VQY, VQZ at time t plus delta t. Then delta V, which is the difference of these two guys, which you can do it, this diagram that we talked about over here. Just draw the diagram. And this, in this notation, you can have this, each component. So this is a vector. So its numbers will be VQX minus VPX, VQY minus VPY, VZY, VQZ minus VPZ. So each of those things go separately. And of course, we are using this shorthand notation. So this is going to be delta Vx, delta Vy, delta Vz. And this much change occurred during t to t plus delta t interval. So this whole thing is one information. Okay, so you got to have the time information, because just how much change is okay, but you should carry along how much time it took to have that much change for quantifying the full effect. All right, so that's going back here. So we did this. Now we're going to do average acceleration. So this information that we wrote down here can lead to a rate of change. So rate of, because I kept the time, not only how much change took place, but I kept the time with it, so I can figure out, and we'll call it average rate of change of velocity in that in the interval t to t plus delta t. Cool. Okay, very nice. So what we'll do is we'll call it average acceleration. Average, just to remind us that this is, I did not take the limit. If I take the limit, then it's going to be instantaneous as before. This is just the average. So several ways to write that. This much change occurred in this much time. So this is abstract and no calculation can be done. So you can draw pictures and things like that. So like I have so I had a VP this way, and No, not that way. Is it true? Yeah, I drew it like that. Oh, it was this way, so yeah. Okay, let me draw this. Continue the same example. So you had a VP that way, VQ that way, and from this tip of this to that was delta V. So acceleration will be in the same direction, but it's going to have its own scale. But so the unit of this thing is meter per second per second. So meter per second per second. So you need its own scale, maybe scale like that. So so you got to need your own scale. So how much is 1 meter per second? How big is this? That requires a scale. A scale of drawing 1 meter per second acceleration. So is this big of 1 meter per second, or is this 1 meter per second It's up to you. You want a big drawing, small drawing, whatever. So scale is needed, and the direction will be the same as this guy, because I'm going to divide by a positive number. Delta t is positive here. Delta t is greater than 0. So I'm going to, this guy remains the same. If the delta t was negative, it's going to have to flip. Okay. So that's just abstract stuff. And you can see I can go in there, delta V, I can go there and divide each one of these by delta t. Delta Vx, delta t, delta Vy, delta t, delta Vz, delta t. Now when we do simple problems in physics initially, we start with like this is 0 and this is 0. Then we just have to deal with that, non-zero. That's called one-dimensional problem. Then sometimes we say this is 0, this is not 0, this is not 0. That's the, if this is 0, this 0. So in this case it's one-dimensional problem. In this case we say a two-dimensional problem, or in a plane in a problem in a plane, problem on a line. So those are our simpler cases, but you should learn the most general first before you start to do the simple one-dimensional problems. Conceptually, it's better to think. All right. So this average acceleration, but you may want, so here is our trajectory, here was P, here was Q. I want acceleration here. I don't want acceleration over this period of time. What's happening over here? So this instant t and this instant t plus delta t. So the way to do is the same thing. You bring Q earlier and earlier until you get very close to P but not on P. Okay? By average acceleration as you choose Q as near P as possible. But not coincident with P. Not on P, but get close to P. That's the idea of limits, right? So we've done this earlier. So that's going to be acceleration at t. This will be also a vector. This will be limit delta t goes to 0 of this average thing, then do delta v over delta t. This is totally abstract. So you go do limits in each one of them, and then you would end up with Vx you're going to end up with derivative dvy dt dvz dt. And of course, just like we had a velocity vector at instant t was dx dt dy dt dz dt, right? And we choose to abbreviate that vx vy vz. We can abbreviate this ax ay az. So this is a vector quantity. Because this is a vector, we need 3 numbers. Even if like this is 0, maybe this is. So if this is equal to 0, and this is not equal to 0, then this will be 1D. And this is not equal to 0, but this equals, that will be 2D. 1D, 2D problems. Okay, so that's this acceleration that we wrote down at an instant is instantaneous. Kind of confusing word to spell. Acceleration. Almost all the physics equations are written at instant by instant. Okay. So when you come in the later, we're going to do F equals to ma. This actually at instant t. Nobody writes it so like this at instant, mass at instant. So this has to be independent to be this to be correct. But if mass was not constant, so this will be actually not correct equation. That's why this is a correct equation. D by dt, mass was varying, then you have to do this. So this is correct. This is correct only if mass is not varying. That's why this thing, you can't use it in rocket motion problems, because rocket fuel is leaving and rocket, the proper, is actually losing mass. So you have to use this in the rocket motion problems. It tells you that this is more fundamental equation because it's true everywhere, wherever Newton's laws are applicable. Okay, Newton's laws are not always applicable. For instance, in very high relative velocity near the speed of light. So if you do a special relativity, this would have to be modified. But for all other cases, we can definitely use Newton's laws. And this is the correct one. And so this is at instant. So if you're thinking instant by instant, you should start thinking instant by instant all the time. If you're not thinking like that, then actually you're shortchanging yourself. In physics, we always look at what's going to happen this instant, that, because things can be different and you have to kind of track it. That is a very important skill to have, to be able to think in terms of tracking the motion, not just equations, but tracking the motion. Okay, so we did this, and let's look at what time it is now. If you can do a special motion today, or we have to perform till tomorrow. So